Bob has an undergraduate degree in meteorology from Penn State. He then went on to Delaware, received a master's degree and PhD in climatology. But despite not having a degree in geography, he's been...
degree is geography.
Oh, it is?
Yes, sir.
I learn something new every day. Well, anyway, he's been active as heck in AAG from day one, and he went on immediately to become faculty at the University of Virginia, where he's been for 31 years. I know him as one of the young bucks, and it's 31 years he's been at one location, but time goes fly. Bob's been active in AAG. He's been active in International Society of Biometeorology. He's been editor of Climate Research, associate editor of various journals, won the awards you're supposed to win along the way, published in the right places, you get it. And among other accomplishments, one of his PhD students is in the back here, Dave Hondula. All right, today we're going to learn about one of the things he deals with. It could be something about circulation, it could be something about storms, it could be something in synoptic climatology. But no, it's about weather and health. Bob?
I don't need that, but thank you very much.
Oh, you don't need that?
I don't need that, do I? Thanks, Bob, for that very nice introduction. As he said, when I was a graduate student, I was involved with some contract work up here in Arizona. We made a number of trips out here. I probably met Bob when I was a master's student. I've known him for a long time. Around the same time, probably, Randy Cerveny. I guess we're about contemporaries. Maybe you're a few years older or younger. I'm not going to get into that, but I've known Randy for a long time. Tony has helped my career in a number of unmentioned ways over the years. And Tony, I'm forever grateful for the things you've done for me. Good friend. Pleasure to have Dave here. As he mentioned, I'm in Deirdre Pfeiffer's office. I will be here till early July. If you want to come by and chat, if you want to buy me lunch or dinner, invite me to your home. All good ideas, so yeah, please do over the course of the time I'm here. So today we are going to be talking about weather, climate, and human health, one of the passions of my research over the years. And just to get things started, here is a time series of daily deaths in Philadelphia over a 26-year period. I ran a 21-day smoother through the data so we can get a better sense of what's going on over the period of record. Each of those vertical lines is January 1st. And you can see pretty clearly that a lot of the peaks in mortality seem to line up roughly around January 1st. A lot of the troughs are about 6 or 7 months later. There seems to be some really clear seasonal pattern to the record. Now, a typical MD who's looking at this pattern will say, I'm going to take temperature, I'm going to remove seasonality using temperature, and then I can go on to do the rest of my research. I think as a climatologist this is the bad idea because temperature is not seasonality. We could argue here that just on first principles that we all know that when it gets extremely hot that fewer and fewer people don't die, right? It's not necessarily the case that the coldest winters are the deadliest winters. And so the notion that just using this correlation between temperature and seasonality to remove seasonality will do it, but for the wrong reasons, doesn't make a lot of sense. There are a lot of factors, meteorological, environmental, human behavior factors that have seasonality to them that could be related and are related to mortality. So you don't want to get your cause and effect screwed up here. So here's a couple examples of just a number of years that I picked out from the record just to focus in a little bit on the mortality record. Oops. The green line here is a smoother through the daily period of record. So we can start asking questions about interesting aspects in this time series. For example, why is mortality seasonal? Is it related to weather or climate, or is it just happenstance? What causes these excursions that are large excursions from the long-term mean signal? Is there some explanation for those that might be climatic? Why do the seasonal peaks in timing vary from year to year, as well as the magnitude of the seasonal peaks? Sometimes we see peaks that are followed by troughs, other times we don't, but it can be a possible explanation for that. And is there something different in fall and spring in terms of the long-term record? So if we're going to understand how weather and climate affect human health, we need to understand what's going on in terms of the seasonal signal and the excursions from that. So basically, that's what we're going to be talking about today. I'm not going to focus on one study. I'm going to talk about kind of the course of my human biometeorological research over my career, hitting highlights, and hopefully by the time you leave here at 4 o'clock, you'll have some feel of how our bodies are affected writ large by weather and climate. So here basically is where our starting point. We have some seasonal signal in mortality with peaks in the winter, with a low in the summertime, and what we're interested in is, can we explain the interesting anomalies from that long-term seasonal signal? And I think we can explain some of them, not all of them. So, let's get started. This is my version of a human being. Some people think it's a turtle, but whatever. This is the way I draw a human being. And of course, we get energy from metabolism. We consume food, and that sustains our body's processes, and that gets us going. But we also have a relationship to our external environment, such that if we're standing in the sun, we absorb solar radiation. We are getting infrared radiation or heat from our surroundings, as well as radiating heat to our surroundings. If our skin temperature is higher than the air temperature, we're losing sensible heat. If the air temperature is higher than their skin temperature, we're gaining it, so that can go in either direction. Sensible heat, conduction, and convection. Of course, we cool off via evaporation, which I'll be talking a lot about. And essentially, when you add all of these up, you would like the total of them to be 0. That's what I'm calling the storage term. So you take all of our metabolism plus the heat inputs and deficits, and ideally, the goal of our body is to keep homeostasis. We want the total of all those inputs and outputs to be 0. When we're not in balance, then our body has to do something to try to achieve balance. Otherwise, our body core temperature is going to rise or fall. This is basic human energy balance. I'm going to mention some people who have dedicated their entire research life to studying this in great detail. And given sufficient measurements, we can actually do a pretty good job of determining the heat balance of the human body. I'm not one of these people, but I just wanted to give you a sense that there's a lot of really good science behind some of the things I'll be talking about today. We, our species, Homo sapiens sapiens, is a subtropical creature, a subtropical animal. Our healthy core temperature is 37 degrees Celsius, 98.6 Fahrenheit. That's our core temperature or rectal temperature. Generally, it's the case that when our core temperature rises to 42 degrees or above, we die. And when it falls below about 27, we have cold mortality. Now, isn't it interesting that our body core temperature isn't set to some point in the middle, like about 34 or 35 degrees? Some people believe that we are suited to live in the mid-latitudes because it's not too cold and not too hot. However, this is not a coincidence. We are close, if not precariously close, to the heat threshold of death, because the human body is much better suited to shed away heat than we are to generate heat. We are a subtropical animal. We survive and live in a hot environment, and we are adept at dealing with those kinds of situations. So the proximity of these two temperatures is probably not coincidental. It's probably evolutionary. Now, when we have a low core temperature, how can that happen? Obviously, exposure to a cold environment. We can do things to our body via drug and alcohol use. Our thyroid might not be functioning properly, all of which that can result in a decline in our body's core temperature. What do? Most of our responses to cold are behavioral and cultural, not necessarily physiological. We wear clothes, we heat our buildings, we build structures to prevent us, to shield us from the wind, etc. So we're not losing a lot of heat in these situations. However, when the body is exposed to cold, the thyroid gland releases hormones that increases our metabolism rate. That's the first response. When we start shivering to generate heat, that's kind of our body's last resort, a process called thermogenesis. So shivering isn't the first thing we do when it starts getting cold, but it's getting to a more desperate situation for us. And we go through a process sometimes of vasoconstriction, which I'll talk about in just a second. Maintaining a constant core temperature in a cold environment is energetically costly to the body. It's a difficult situation that we are in when we're exposed to cold environment. Now, this vasoconstriction, basically the idea here is we've got the skin at the top, And we have a blood vessel going from the heart back to the heart this way. And of course, we have capillaries that are going up close to our skin surface. Now, when it gets cold, the body's main purpose is to keep the heat close to the core. Keep the heart functioning, the lungs functioning, the brain functioning. You don't want to be losing heat through your skin. So you constrict those capillaries and blood vessels that are moving towards the skin, allowing the blood to maintain a high temperature as it goes from the heart back to the heart. Of course, the cost here is that your skin surface is going to get cold, and of course, in extreme cases, it can result in frostnip or even frostbite and subsequent loss of digits that can come from that. But the body is trying to keep functioning, keep the core temperature high enough to go on. Now, we also have something called countercurrent heat exchange. Just real quickly, if our arteries and veins sort of flowed in the same direction, arteries being warmer and veins being cooler, you're going to have a heat flowing from the hot to the cold. So an artery and a vein that are close proximity, the artery is going to lose heat to the vein. Of course, we have, in our bodies, we have a heart from which the warm blood flows through the arteries out to our extremities, and then from our extremities through veins back towards the heart. And so as the blood is moving away from the heart, it is losing heat toward the cooler veins. As a result, the temperature of the blood coming back to the heart is warmer than it would otherwise be. So when we have vasoconstriction, we bring the arteries and veins in closer proximity to each other, enhancing the countercurrent heat exchange and allowing our body temperature to be higher because of the temperature of the blood flowing back to our heart. We see this in our favorite Arctic birds. You can see this little fellow is standing on one leg, smart, because there's no reason to stand on two and lose all that heat. Countercurrent heat exchange is going on here. There have been measurements in the blood temperature of gull feet that is only a degree or 2 Celsius higher than freezing. So it's very cold blood. But this little fellow is perfectly comfortable because countercurrent heat exchange is going on in their bodies. And the same thing is happening in ours when we have a cold environment. So the opposite, high core temperatures. Obviously, exposure to heat. When you're exercising, you eat a lot, and all of a sudden you're like, oh man, it's really hot. Raise your core temperature. Of course, a fever, different kind of set of circumstances there. What are our responses to heat? We, as a species, are very good at sweating. We shed a heck of a lot of heat via evaporative cooling of water on our skin. We also have a process called vasodilatation that I'll talk about in just a second. There is no mammal that sweats like humans. Horses sweat. There are some other animals that sweat, but no animal has the same kind of sweat that humans do. Which brings me to one of my favorite quotes about sweating. There is no one human attribute of more importance than the ability to sweat skillfully. I'm sure some of you in this room know people who sweat skillfully, or maybe you are those people. So people say, boy, you sweat like a whatever. And it's like, no, this is actually a good physiological attribute to have. It's a positive thing, right? And you are Homo sapiens sapiens, you're a subtropical animal. Just keep reminding people of this. This is all a good thing. So we rely a heck of a lot on our ability to shed heat via the sweat response. So vasodilatation, also called vasodilation, depending on how pompous you want to sound, I think. Basically what's happening here is the opposite. The blood vessels, the capillaries will dilate, allowing more blood through. So the warmer blood from the heart is going to be closer to your skin. Now there's an opportunity for you to lose that via sensible heating, conduction, convection, or infrared radiation from your skin. The blood going back to the heart is cooler, thus hopefully maintaining a lower body core temperature. So it's all good. Now, I'm going to be talking a lot today about mortality. I'm going to be talking a little bit about hospital admissions and emergency department visits. I just wanted to point out that if somebody dies from some kind of heat event, there probably are a lot of other people who aren't as vulnerable who are suffering from it. So mortality is really good data to have. You know, a person dies on a date, you know they're dead. That's kind of a clean data set, sort of from a biometeorologist standpoint. Things get messier as you work your way down through the pyramid here, but there are impacts that sort of cascade down through it. All right, now, getting back to the question of seasonality, I did a study where we looked at a bunch of cities in the United States, and we kept track of the cause of death. Now, every time you go to the doctor's office any person who dies or you have a visit to the emergency department or the hospital, you are going to be coded with a discharge diagnosis or a cause of death. There's something called the International Classification of Diseases that contains tens of thousands of specific diseases. Here are the broad categories of those diseases, according to a classification that we worked on back in the 2000s. If, for that particular disease category, it shows up to the right of the yellow line, that means it's more prevalent in the winter than the summer. The 4 main causes of death are shown in light blue. So what you see is that regardless of the cause of death, for the most part, they are prominent in the winter and less common in the summer. The exceptions being injury and poisoning, which is more common in the summer, neoplasms, which is pretty non-seasonal. This is cancers. And cancer has no relationship to weather or climate that anybody's been able to find so far. It seems to be completely non-related. But look at our 2 of our main categories, circulatory disease and respiratory disease, highly prominent in the wintertime. In fact, respiratory disease deaths are 50% more likely in the winter than the summer. So is there some kind of possible climatic relationship to this? Well, here's a plot on the bottom of total mortality over a long period of time in the United States. And above that is mortality from pneumonia and influenza. Now, these 2 diseases are oftentimes combined because people that get influenza are often not diagnosed as having the influenza, but they subsequently get pneumonia. So they're highly correlated with each other. And oftentimes we don't even bother testing people for influenza if they already have pneumonia, so they're closely coupled. Well, you can look at these and you can see, boy, there looks like they line up pretty well. Total mortality was high in the winter of 1981. So was pneumonia and influenza. No big peak in 1982, no big peak in total mortality, et cetera. In fact, a gentleman named Reichert subsequently did a study for heart disease, cancer, pneumonia, cardiovascular disease, diabetes, and said that the peaks for everything other than cancer tend to line up, that the time series are all tightly coupled, and they have the same kind of time series model that would describe them. And he wrote the following conclusion, which I think is a bold statement to put in an academic journal, so I applaud him for being out there. We believe that the singular cause of excess winter mortality is, in fact, influenza and the diseases that are related to influenza. So remember, our entire curve is highly seasonal with a big peak in winter. Is it possible that that's all influenza driven? And if so, is there a relationship to weather? Well, maybe. I thought there might be. I'm getting a little bit ahead of myself here. Just to convince you how the seasonality works, the top graph here, the pie chart is showing blue for December, January, and February. The warmer colors are northern hemisphere summer. This is influenza in the United States at 39 degrees north. There's Mexico. By the time we get to Colombia, you don't see much seasonality. It's pretty evenly distributed across the different months. There's Brazil, there's Argentina, June, July, and August. Clearly, influenza is a wintertime disease. Interestingly, I was at a couple meetings of influenza people, and they don't understand why influenza is seasonal. It just is. So, possibility of a climatic link here. Big deal, because influenza kills a lot of people. 41,000 annual deaths in the United States from influenza alone. 200,000 hospitalizations, 250,000 to 500,000 global deaths. And of course, as you know, it's spread by person-to-person contact or coming in contact with a live virus and getting it somehow ingested into your body. So this study caught my attention. 2007, some people put guinea pigs into cages in a controlled environment. Guinea pig lungs are somehow similar to human lungs. According to my respiratory disease friends or colleagues that I've worked with. Basically, they infect the upwind guinea pigs with influenza, turn on the fan, control the conditions in the chamber, and see what happens to the downwind guinea pigs. So you're controlling the temperature, they're controlling the relative humidity, and looking at the infection rate. And the results are shown here. At 20 degrees, the infection rate was higher when the relative humidity was 20 or 35%. At 5 degrees, the infection rate was high pretty much at all temperatures. And they used relative humidity as their moisture variable. Should have consulted with an atmospheric scientist. Bad choice because of its collinearity with temperature. But nevertheless, they concluded and that's a matter of another talk that I'm going to get into today, cold and dry air enhance airborne influenza transmission in guinea pigs. So here's a climatic connection that is potentially interesting. So is there any reason to suspect this? Well, you can read the slide. I'm not going to go through it. But there are aspects of virus stability that are related to temperature and humidity. The ability of our lungs to repel an ingested virus can be affected by how dry the air is. There are behavioral components, like the time when it's cold, people tend to spend more time indoors and perhaps have the opportunity to infect each other. The return of children to school, classes in September. You always read about this. Nobody's ever tested it, and it's not proven in the literature, but it's out there. So probably for a multifaceted number of reasons, you can make a relationship that cold and dry air is theoretically possibly related to influenza transmission. So we can hypothesize then that either cold, dry, and/or cold and dry seasons or cold and dry periods within a season could be correlated to peaks in influenza, death or mortality or morbidity, I should say. And so the problem with this, as I'm going to explain in the next few slides, just to give you a sense of the kind of research I'm doing here, is that we have unknown and variable lags between the time of potential infection and the time of the human response that we have to understand. So this is pretty straightforward, but just hang with me for a second here. Let's just say that we have a sudden cold, dry air outbreak on the 1st, okay? This is a potential date when we would start seeing influenza infection or pneumonia infection. There is a latency period between infection and the time that you know you're sick. For influenza, it varies from about 24 hours to 4 days or so. So perhaps person number 1 will start seeing symptoms on the 3rd. They don't like going to the hospital, but they go to the emergency department about 5 days later, and then perhaps this person will die on the 19th. So now we have some data. I've got a data point on the 9th. I've got a data point on the 19th for person number 1. Same cold, dry air event affects person number 2. Here they are. The latency period was longer. This person, as soon as they get sick, go to the hospital. They died on the 16th. Okay? Same weather event produced these 2 cases. Patient number 3, you know people like this. They got sick right away, didn't go to the hospital, didn't go to the hospital, didn't go to the hospital. Behavioral choice, right? Went to the hospital, died a couple days later. Person number 3. We have to come up with a way for all of these to be related to day number 1, right? Human behavior is going to be a factor here in determining certainly a hospital admission date. And there's going to be just inherent variability in the process because we're dealing with people. So just to give you an example, I came up with a mortality time series using synthetic data of 200 deaths. Let's say these are just the date. We're using day 1 as our date of putative infection, and then this is the time series. If we smooth this, we can get a sense, and here I used a 17-day centered moving average filter. We pass that through the data, and we can see the peak occurring in this data set around days 15 through 19 or so. Now that's a centered filter, but there's some lag between day 1, when the weather event occurred, and day whatever, when the person died. So we can actually use a leading filter and lag everything forward, and now we can start getting this lined up with the time that we believe there was a weather event that could potentially be related. Now, to complicate matters, here's day 2. This might be another cold day, and these people are going to be going to the hospital or going to be dying, etc. So we're dealing with kind of messy data here. And the smoothing and the lagging is a necessary component of the work that we're doing to understand the process. Okay, so getting to specifics now. New York City, we had a long time series of mortality and pneumonia. We picked a threshold based on the distribution of the data, and we identified a number of episodes that were pneumonia and mortality related episodes in the long time series for New York. We can then go back and look at these and see, is there a relationship to weather or climate during these periods? So this is a really good slide, I think, because it's just a visual. There's no statistics behind it, right? So all we're looking at, the top is using this 17-day leading smoother. You can try different smoothers to find the one that works best. We use 17 days in this case. And below that, in red, we have dew point temperature with the shorter term smoother through that. So you can see here, for example, in 1980 in New York City, here is a mortality peak, and here is a low dew point period, dry period. They line up. 1981, bad year for pneumonia and influenza mortality. There's a dry period. 1982, no mortality peak, no obvious dry period. Same for 1983, et cetera. There's a nice case in 1985. I think just looking at that visually without applying any statistics or anything, you can see there's probably some kind of relationship between how dry the air is and using this 17-day lag when people are dying from pneumonia and influenza. Here's when we run the stats, we get a plot that looks something like this. On the left is event duration. On the right is event mortality. And you can see that when you have lower morning dew point temperatures, when the air is drier, it's linked to higher mortality and longer episodes. So the evidence has become clear, I believe, over the past 5 to 10 years that there is a weather link to influenza transmission. I'm not at all saying it's the only cause. I think it's just one of them, and the causes are probably multifaceted, but a number of different researchers for a number of different cities have found results like this. We looked at some different cities in the United States, looking at pneumonia and influenza events, the maximum temperature and the dew point during those events compared to non-events. In every case, Chicago, Phoenix, Philadelphia, Houston, Detroit, the results are very clear. Cold air and dry air are associated with higher pneumonia and influenza deaths, right? So, evidence is coming out that accounts for possibly this part of the time series. All right, now, what about the summertime? This is what everybody worries about here in Phoenix. Anybody can get through the winter in Phoenix, right? No polar vortex or anything like that coming by, right? But summer, where are all the out-of-town visitors in the summer? That's what you'd like to know. I don't have room for you in February, but if you come in July, we have plenty of, oh, no, I'm sorry, I'm washing my hair in July or something. I can't do it. Well, anyway, what's going on in July? This is the time of year, or in the summer, this is the time of year when we should have the fewest deaths. But of course, we know when we have heat events, that's not the case. Just going back to some work I was doing early in graduate school. This is a simple plot of daily deaths versus afternoon apparent temperature in Philadelphia. Apparent temperature is a combination of temperature and humidity, so it's also called the heat index. This is the kind of plot when you're excited and you get your all data ready to go and you plot it up, it makes you want to become an economist, right? It looks like a terrible data set. I want to change my major. I don't know why I picked economics. Long story, but anyway. You're looking at this and you're like, there's nothing here. However, there is something here, and it's something very interesting. If you take the average deaths at each temperature as you work your way across the plot, you get a curve that looks like this. It's U or J-shaped. Take the mortality data for any major mid-latitude city in the world, and you're going to see this same kind of plot. It's a U or J-shaped plot. This is one of those things in health that is truly generalizable from one location to another. So we have the seasonality that we would expect to see with higher mortality at the tails of the distribution. But remember, there's seasonality in that data set. So if we take the raw data and remove the seasonality, we kind of flatten that U out a little bit, like we have here. In this case, for this data for New York City, there's still a little bit of a winter peak, but there's a very obvious summer peak. So we can then ask the question, is there a temperature beyond which we start seeing an increase in mortality in our given city? And so we can calculate that using statistical analysis that's fairly straightforward by looking at class intervals and determining at which temperature we begin to see a mortality peak. For this case, we can say it turns out to be a 30-degree Celsius apparent temperature for, was this Philadelphia or New York? New York. And of course, you can do that for a number of cities, plot them up, and you get a map that looks like this. This is the temperature, the apparent temperature beyond which people start to die in the summer. Now, what you don't see is the same number everywhere. You see that that threshold is relative compared to the climate of your location. For years and decades, the National Weather Service used the same heat index for the entire country. So whereas you might have a heat index, a heat event in Minneapolis that's saying, watch out, basically you're under heat warning in Phoenix from April to October. Not a good idea. As you can see from these data, the threshold temperature for Phoenix was a very high 44 degrees. But it's in the upper 30s along the Gulf Coast and in the low 20s or upper 20s and 30s in the northern tier. So the response to heat is relative. Clearly, there's an acclimatization effect going on here, an adaptation that's taking place from one location to another. This is sort of an aside, but my major professor, Larry Kalkstein, and I did some research on this back when I was in graduate school. We published a paper in the Annals in 1989. We had a map that looked like this, and some graphic designer for the Annals said, wouldn't it be cool if we made little thermometers for each station? And so we'll have one for Boston and Philly, and Larry said yes. As a result, you get a completely useless map with a bunch of sticks pointing up where you have absolutely no information whatsoever. So the moral of the story is, don't listen to the graphic designer who's trying to tell you how to publish your research, okay? Just do the right thing, because that was really a dumb decision. Well, I love Larry, he's a great guy, but this was not one of his brighter moments when he agreed to this. All right, so the question is, as we move from place to place, there's some kind of acclimatization taking place. So let's talk about that a little bit. Definition is the long-term response over the lifetime of an organism, human, to a suite of variables to reduce the strain caused by environmental stressors. So think about this. Heat-acclimated individuals, people who are accustomed to heat from exercise or from living in the desert, for example, they have lower heart and metabolic rates, they have lower skin temperature, lower core temperatures during the heat, they sweat more profusely, sweating starts earlier, and it's more dilute. It doesn't have as much salt in it. There's more vasodilation or vasodilatation, depending on your preference. And when they're exercising, they don't feel the exertion as much as somebody who's not acclimated. Good news for all you desert dwellers here is that although exercise hastens this, all you need to do is spend 2 or 3 hours a day, about 3 days a week in the heat, and there will be a biophysiological change to your body. You will become heat acclimated, okay? So just sit outside for a couple hours, not exercising, and you're still going to get an acclimation effect. And more good news is that it's easier for you, desert dwellers, to go to a hot, humid environment than it is for somebody like coming from Miami to move to the desert. There's more stress placed on their body than there is on yours. So you are well adapted to living in a hot place. Duh, you came to a seminar to hear that. Been living in a hot place for a long time, no kidding, right? Now the question that has befuddled bioclimatologists for a long time, and is still, I think, somewhat uncertain, is what is the rate at which we acclimate to heat? The literature seems to be converging on the notion that it takes about several days to 2 weeks, and that process continues over the course of a month. But if you move away from the heat and you have no exposure, then you lose those benefits after about a month or so. So you have to keep remaining in this kind of hot environment to get the benefits of acclimation. Now with the cold, the research is a lot less clear, but it seems it's more of a behavioral avoidance response than it is the body actually acclimating to cold. But some studies suggest that shivering will occur at a lower temperature. There is less vasoconstriction in the hands, so more blood flow to the hands to people that are working outside in the cold to sort of keep their hands nimble. Changes in the blood and heart rate are going to occur, or increase, but not as rapidly as somebody who's not acclimated, and once again, the decrease in perceived exertion. Interestingly, a person that acclimates well to the heat does not necessarily acclimate well to the cold, and vice versa. So you might be great in the desert, but not do very well in the Arctic. It's just a difference from person to person. Okay, so we were looking at mortality over time. The questions we were asking was, is there a trend in deaths over time when you have exceedances above the threshold temperature at a given location? So for the data we had at the time, we combined the 1960s and 70s. We ended up with 10 years over those 2 decades. 1980s is the middle bar. The 1990s is the bar on the right. And basically, this is mortality above the threshold temperature over time. And you can see that in almost all cases, heat-related deaths have declined in the United States. Okay? There's the average across all of the major cities that we looked at in the study. So with few exceptions, this is occurring despite the fact that heat waves are getting worse and they're getting longer. Okay? So what's going on here? Well, a lot of things are going on. One of the main ones is the increase in air conditioning in homes and offices over time. If you break the United States up into these, we had air conditioning penetration data for these different geographic zones. You can see that mortality has gone down and that percentage of air conditioning homes has increased as well, such that there's a pretty strong correlation between them, except for this one region, the mountain region here. And this is basically means we only had one city, Denver, in the mountain region. We didn't have a lot of data there, so it's probably nothing to read too much into. So clearly one of the reasons that we're all here today is because we have air conditioning. Phoenix wouldn't have, how many million people? 4 million? Oh my goodness. Okay. Water and air conditioning. What's that?
We have some Native Americans.
Okay, we count them all. They count them all, sure. Yeah, they did, and they managed to survive okay. So, and clearly they're heat acclimated, I would say, right? The ones that come from the desert. All right, we just published a study last year, just sort of a quick aside here. We were looking at heat waves and hospital admissions at the University of Virginia Medical Center. And we had a good data set that we were able to break down into demographic variables. We had age, we had race, and we had all the 21 major disease categories. And what we found is, well, total admissions are higher during heat waves. Same thing for males and whites. But what we thought was really interesting is, in terms of the age breakdown, it turned out that people aged 20 to 49 had the most significant response, which would suggest that these are people that are working outside who are exposed to the heat, and they're going to the hospital, being admitted to the emergency room during these heat wave events. And there have been some other studies at other locations that found a similar result to that. Okay, now, we have a heat wave that comes along. This is the population and the vulnerability, this is the vulnerability of the population. Heat wave comes along and it kills the most vulnerable people, leaving behind a healthier population, right? The theory would be that subsequent heat waves would have less of an effect on the people remaining than the ones who have been culled during the heat wave. Now, this effect, then, you should see a decline in mortality in the days following a heat wave. This used to be called harvesting, which is not a very nice term for death. Nobody wants to hear grandmother was harvested by the heat. She won't be with us anymore. So we now call this mortality displacement, where simply the question is, were the people who died here going to die anyway? Their death just occurred a few days earlier than it would have because of the heat. Okay? So nobody had really studied in a systematic manner mortality displacement. So we set aside about to do that. Just to give you a sense of what's going on here, here is a plot of the relative risk of mortality is the z-axis, and here we have lag. This is temperature. So if you look here, there's our typical U-shaped relationship that we see at zero lag. So here's our heat-related mortality peak. At high temperatures, we're seeing higher mortality. But look here. About 4 to 6 days out, we see this dip in mortality. That is the mortality displacement effect. So when you read some journal article or perhaps some news report about how many people have died during a heat event, the question that you might ask is, well, how many of these people were going to die anyway? Or are you just counting all the people that died? I should point out, by the way, that very few people are actually diagnosed as dying from heat stress. Normally what will happen is you're going to be affected by the heat and you'll have a heart attack or a stroke, and it will be categorized in those categories. So when we look at mortality, if you just pull out heat deaths, you're really, really missing the boat. You need to look at total mortality and the deviation from the long-term signal. But anyway, you're going to get numbers for this, the impact of a heat event. So if we account for mortality, mortality displacement, what would happen? So here's the way we did this research. This is maximum temperature anomaly from the mean. On the bottom, we have mortality anomalies. Let's pick a threshold. We'll say we'll take the 80th percentile. We'll identify a heat wave as 3 consecutive days above the 80th percentile of a maximum apparent temperature. Okay, here's a heat wave. Let's see what's going on with the mortality during that heat wave and after it. Looking at the subsequent 15 days, we can then calculate mortality displacement as the sum of the negative anomalies divided by the sum of the positive anomalies over that 15-day period. So we're going to get a number for the 80th percentile. then we can change that. We can do it for the 90th percentile, the 95th percentile, the 97th percentile. As the heat wave becomes more intense, how does mortality displacement vary? And so here's what we get as an example. Once again, here's Philadelphia. On the x-axis, we're increasing our apparent temperature threshold, and our y-axis is the mortality anomaly. So here we're counting our positive deaths, excess deaths, on the black line, and the lighter line here in the bottom is what my co-author of this paper called negative deaths, which I never was able to wrap my head around. I'm not sure what a negative death is, but we now call them negative anomalies. That makes a little more sense. And all we're going to do now is divide this by this, or this is the numerator, this is the denominator, and we get the mortality displacement. So essentially what we have here is mortality displacement as a function of threshold temperature for that particular heat wave. If there's no heat-related mortality at all, in other words, if all the deaths are displaced, the value is 1. If there are no displaced deaths, heat wave comes along, and all those people who died or were not going to die anyway, then the value is 0. And what you can see here is a clear decline in the mortality displacement as you increase the apparent temperature threshold. So essentially, at low apparent temperatures, the mortality is minimal, so most of the deaths are simply displaced deaths. As the heat wave gets more severe, you can see that the top line is increasing at a more rapid rate than the bottom line is decreasing. So as a result, we have a decrease in mortality displacement. So for example, in this case, at 37 degrees, about half of the deaths were new and about half of them were displaced. So that would suggest that if we said 3,000 people died on that day, or that period, that heat wave, it's probably 1,500, and the other 1,500 were normal deaths that were just displaced a few days in time. Tragic nonetheless, but just displaced in time, right? So we did that for a number of different cities. Apparent temperature threshold for the different cities. This is the mortality displacement. And you can see, for example, at about a 97% threshold, the numbers vary from about 50 to 80%. The bottom line being, there's a lot of people dying during heat waves, but many of those people were going to die anyway, and if we're going to get accurate counts, we need to factor that in. So that's the summer, right? Now we know. Increase in mortality during heat waves, and in some cases we have a mortality displacement effect that follows that. Now what I've been working on most recently, and I'll be finishing up with this, is some possible interesting things happening in the spring and the fall. And this gets us around to talking a little bit about acclimatization. Working with something called the Acclimatization Thermal Strain Index, or the ATSI. Stress is the net thermal load on our body produced by some external environmental factor. Strain is the biophysical response to that stress. So we might get strain from the heat, and the body's response would be sweating. That would be the stress. The strain would be the sweating or the increase in heart rate or something like that. Did I get that backwards? Stress is the temperature, strain is the response. Now, of course, if we put our body in a cold environment, we're going to put on more clothes, we're going to put on gloves, we're going to put on a hat. However, our respiratory system is unprotected. We're going to breathe in the ambient air, and we're going to exhale whatever air is produced in our lungs in that process. So we can protect the rest of our body, but we can't protect our respiratory system. Therefore, you would expect that the first indication of physiological strain would be felt by the human respiratory system. So we can look at that. In cold conditions, what happens to our respiratory system? Well, our bronchia will constrict. They don't want that cold air to get as deeply into our lungs for reasons that I don't really understand because I'm not a pulmonologist. But that's bad for our body because our body actually needs more oxygen in cold weather, not less. So this is going to produce a physiological strain on the human body. This vasoconstriction produces this kind of feedback where we're not getting enough oxygen and there's a physiological response. Now, people can become acclimated, of course, to less oxygen. You know this is true in mountain climbers, for example. It affects their breathing rate. They have more mucus glands in their lungs, and their heat loss compared to a non-acclimated person is 25 to 40% less. But interestingly, typically for the respiratory system, about 15 to 30% of our body's heat loss is through the respiratory system, and in some cases up to half. So one of the keys here to heat loss, particularly in a cold environment, is what's going on in our lungs. Now, the idea behind the ATSI is that what happens when a person is acclimated, for example, to cold, and all of a sudden we get a hot spell. That should produce a physiological strain on our body. And similarly, what happens when we go from warm to cold, or there's a cold spell in the middle of summer, for example. Well, a person will suffer strain that results from a lack of acclimatization to the new weather condition. So you can do some calculations on this based on the ATSI, the heat exchange between the lungs and the ambient air. So what we're doing is the heat exchange can be calculated as the sum of the sensible heat and the latent heat exchange that takes place in the lungs. Okay? Total heat exchange is sensible heat plus latent heat. And we can make estimates for the human body of how much heat is exchanged sensibly and via latent heating in the body by making assumptions about the volume of air inhaled, the temperature of the exhaled air. Typically, regardless of the temperature of the air that's inhaled, we're going to exhale at about a degree or two below body core temperature. So when we inhale cold air, our body has to warm it up. And the air we exhale is almost saturated as well. So your body has to warm the inhaled air, and it has to humidify it almost to saturation. So these numbers, the exhaled temperature and exhaled vapor pressure, are pretty much constant. I mean, they vary obviously a little bit from person to person, but we have a pretty good idea. So really the key factor here in determining the heat exchange is what's the ambient conditions. What's the ambient temperature and the ambient vapor pressure that is going to determine how much heat exchange takes place in the lungs. You can calculate this and come up with an index that looks at the acclimatization that's taking place. So the idea here is all we're going to do is look at the difference between the heat exchange of an acclimatized person to a non-acclimatized, or the acclimatized state to the non-acclimatized state, and divide by the acclimatized. Or, if we're thinking of this temporally, we're assuming that you used to be acclimated to the conditions, but now you are not because you're in a new environment, and you can divide by your previous state. You come up with an index. So the way this works is if the ATSI is close to 0, you are fully acclimatized, and you're experiencing very little strain. However, if it's negative, you're going from a hot or hot humid to a cold or cold dry environment, and vice versa. If you're going from cold dry to hot humid, the value is going to be positive. Okay? So we can look at this and see if there is any kind of relationship to data for mortality or morbidity. And so we had, this was really the first application of the ATSI. It was built for a kind of a climate and tourism context. You know, what happens to people from Saudi Arabia when they go to Nome, Alaska, right? But we thought there might be effects at the shorter time scales, and you don't have to go to those kinds of extremes. So once again, we went back to the UVA Medical Center, and we looked at respiratory disease discharges as a primary discharge. Here we have admissions by month, and what's interesting is you can see admissions are highest in September. And in Charlottesville, this is when things start getting cooler, right? And you also notice, if you look carefully here, this is October, April, and November. All these transition months have higher admissions. So it gives you some reason to think there might be something going on here. If you plot the same data up versus ATSI, you see what happens. As you see, September, October, November, all are negative ATSI, which you would expect because you're going from hot to cold, and they have high admissions. And it looks like Canis Major. Coincidence? Ancient alien theorists think not, right? Yeah. So, if we look at daily admissions, daily ATSI, all we're doing here is saying, here's the change in ATSI from day to day, here's the admissions. We got no relationship. What I theoretically would have expected was for a peak here when you're going from warm to cold, and a peak here when you're going from cold to warm. We didn't see that. However, once we started looking at a longer time scale, when we started using a 7-day smoother, or 5-day smoother in this case, now we kind of see that relationship. Negative ATSI show higher admissions, And you see a little bit of a peak for positive ATSI values as well, those not as strong. And this is a statistically significant relationship here, right? At a longer time scale, now we're approaching kind of seasonality. We start seeing the same kind of relationship at the cold end, but not so much on the warm end. So just to sort of summarize this, as you go from hot to cold, you're not seeing something at the day-to-day scale, whoops, but when you get to the longer time scale, weekly or biweekly or monthly, you're starting to see a peak in hospital admissions. So this could be based on the rate of acclimatization. We said that's about 4 or 5 days to 2 weeks. Well, non-acclimatized people will start responding at that time scale. So we believe this is representing a lack of acclimatization of the population. They're used to summer. Here comes these cold blasts in winter, these Arctic blasts, cold polar vortex coming, right? What we should see after the polar vortex is next week and the following week, a bunch of increase in hospital admissions. That would be a good test of hypothesis, wouldn't it? If I didn't have anything else to do, I would look at it. Maybe we'll get Tony on that. Tony looks like he's looking for a project there. Now, what about the other direction, cold to hot? We didn't find it. In fact, we saw actually reduced admissions when we got to longer time periods. So the body goes under more stress as you go from a hot, humid environment to a cold, dry environment. And these transitions produce a stress and a strain on the body's respiratory system. So I think we can close the loop now on our seasonal tour, right? It's not simply temperature, right? We know that in winter we have peaks that are related to pneumonia and influenza and comorbidities associated with them following cold and dry periods when influenza airborne transmission could very well be enhanced. In the summer, when we should have the fewest deaths, we actually have increases relative to the long-term mean because of heat-related stressors. But we always remember we need to keep track of short-term mortality displacement or grandmother harvesting. And the transitional seasons, physiological related strain, related to this ATSI. This is new research that I'm just beginning into. I'm not as convinced of it, but I think we're on the trail of something that might be fairly interesting. So everything I talked about, here, is in one of these papers, and I think I remember all of the references that I used in preparing the study. But of course, if you have any questions about any of this, I can be happy to refer you to the literature. So thank you all very much for attending my talk today, and I wish you well. Thanks for coming. And there's my email address. I'm still using my UVA address, so I'm happy to correspond with you. All right, thanks. Bobo. I'm happy to take them. Yes, sir.
Much of your data, I presume, is aggregate data for the population.
Yeah, we're not, yes, go ahead, repeat your question for the worldwide viewing audience.
Most of the data that you've got is aggregate data for the population.
Yeah,
is there any...
Yeah, I'm sorry, I was going to say for health data, you get to HIPAA issues regarding data about individuals. So there has to be sort of a minimum sample size of counts.
So,
yeah.
But have you been able to in any way break it down by gender, age?
Yes.
I mean, I'm sure you've thought about this a million times.
Yeah, in some of the studies, we certainly have. In fact, in most of the studies, we've broken it down by gender, we've broken it down by age category, we've broken it down by race and ethnicity, all those kind of things you would normally expect. And obviously, the results depend on what question you're asking, right? But yeah, we always look at those factors when we can, as long as we have a large enough sample size.
I mean, I would imagine if you're elderly, maybe in bad health, all that stuff,
yep.
You're just going to be so much more vulnerable.
Yes, well,
than if you're a 25-year-old able to run a marathon. And
absolutely, absolutely. And it's a biophysiological response. I mean, elderly, it's well known that the sweating response is not as good in infants below or children below 6 months and elderly. So as you get older, you just don't sweat as well. And because sweating is the main way that we use to shed heat, then elderly are more vulnerable to heat stress than somebody younger. That's just one example, but absolutely that's the case. Yeah, yeah, Randy.
Do large magnitude events follow the same kind of patterns here? I'm thinking like, would the Spanish flu follow these kind of variations that you're seeing, or would the size of the magnitude of the event overcome the climate
Well,
considerations?
yeah, I mean, obviously, any kind of major flu pandemic like that is going to have multifarious factor or multifaceted factors that are going to affect it. We have, I'm trying to think when we had the last sort of major pandemic. Well, there was a pretty big one, what, 2013 or so? I can't recall what I guess the answer to the question is I don't know from the most recent case if that followed very closely. That's a good question. We obviously, for some of the earlier ones, we would have a hard time getting the data, but maybe we could piece something together. It might be worth looking at, yeah. So I think that's an interesting question, Randy, and I'm going to take a look at it, yeah. Hi, yes.
Yeah, hi.
Thanks for coming.
So first of all, thank you so much for your interesting presentation. I've learned a lot. The first question is directly related when you were talking about the temperature exchange between our body and atmospheric temperature and things like that. I'm just wondering if in a very cold condition, very snowy condition and icy cold weather, when we touch our tongue with a metal pole, and it sticks within a few seconds, and how do this, body exchange and temperature?
Yeah, first of all, I would not recommend you do that. Yes. So what's your question again?
Well, I mean, I'm just thinking that, because the pole is so cold and your body heat is basically absorbed directly over there and then melted first. But because the temperature is so cold and it's basically thickened really quick and I'm not really sure that's my answer. What do you think about that?
I mean, I haven't done any tongue-to-pole testing. I tried to get Dave to do it when he was an undergraduate, but that's the kind of project you would get undergraduates to do.
Yeah. I think that is... No,
but what's going to happen, of course, is you're going to have heat transfer from the hot object to the cold object. So your tongue is going to be losing heat to the pole. Now, why it sticks, I don't know sort of the tongue physiology, but I could imagine there's probably a pretty good reason for that. But yeah, to be able to release it, you need to sort of heat up the pole enough. I mean, yeah.
Yeah.
You're getting way outside. This sounds like an engineering question to me.
That's okay. I'm just wondering. I'm thinking weird stuff. But the second one is, it's not directly related to your presentation. I'm just wondering if I can model it for the entire continental United States, so 30-meter resolution, particulate matters 2.5, particulate matters 10, or aerosol optical depth, if I can model, hypothetically. If I can process for the entire United States, the data set is not yet available. I'm just thinking, if I can model and process it and predict it, can we get to link with some kind of, number of people killed by pollutant loads, which is one of the highest rates above, diabetes or cancer or HIV or hypertension, and so. Yeah,
you're asking a very interesting question, and it's one that has been at the befuddled biometeorologists, bioclimatologists for a long time, and that is the relationship between air quality and heat, right? For a number of different reasons. When you have a heat wave, the air quality is usually bad in the city as well. And so there are a lot of people that believe that people aren't dying from the heat, they're dying from the poor air quality, and then there's another camp that believe it's the heat and it's not the air quality. So what you can try to do is look for heat waves that have good air quality and look for poor air quality days that aren't in heat waves and try to do the relationship. Unfortunately, there aren't many of those off-diagonal cases to look at. So it's still an issue that hasn't been sorted out. I think it's fair to say that the collinearity between high heat and poor air quality is significant and always needs to be accounted for. If you start reading the health literature, you'll see, if it's a heat wave study, they'll say, I remove the effect of pollutants by putting a pollutant term in. And if it's a pollution study, they'll say, I remove the effect of heat by putting a temperature term in. So this really isn't answering the question, right? It's kind of dancing around the question, but it's a very interesting one. And I didn't mean to not talk about air quality. I've done some work on air quality. It just wasn't part of my talk today. But your point is very well taken.
Hey, Bob, Oscar has one question. Let's finish with that.
Go ahead.
So we looked at all these cities in the North American context. and I guess also down the line through the Western Hemisphere a bit there. I was wondering if it held for throughout the globe too.
Yeah, I mean, obviously, it's going to depend on the sort of socioeconomic situation of the place you're looking at, you know, and is it a monsoonal climate? Is it a lower high latitude climate, et cetera? You find, for example, similar results to the United States in major cities in Australia. You're seeing some similar results. There's a lot of research being done in China that are quite similar, but not a lot of good data coming from Africa, from many parts of Asia so far. So, you know, it's a big question with any kind of health research is it generalizable? And for some of these things, we think it is, but there's a lot of questions we don't understand yet. So there's a heck of a lot of research being done in other parts of the world to see to what extent many of these relationships are, in fact, generalizable. Yeah.
All right, Bob. Thank you very much.
Okay, Bob, thank you.
Yeah. Good work.